Okay, today we talk about something called complex numbers. You guys know what letter we use to talk about complex numbers? I. Okay, so we're going to talk about what I means and how we're going to use it in terms of finding zeros of polynomials. And I've just highlighted 3 sections up on the board. What happens at the end of these next 3 classes? We review for our test number 3, and then we take our test number 3, okay? So on what day of the week is test number 3? April 27. When is that? What day? This is not supposed to be the hardest question of the class. On what day of the week is the 27th? All right, a few votes for Friday. Yes? Yes. So 1 week from this coming Friday is our test, okay? Maybe one question on the test will be, what day is this? And then, okay. So today, we talk about some more stuff about zeros of polynomials. We've been playing this game with zeros of polynomials for a few classes. And then next class, we really change gears and we start talking about exponential functions. And you can see 2 classes about exponential stuff. And then we'll have our test. And then we've got like a week and a half left between the 3rd test and the final exam. And in that week and a half, we talk about logarithms, which some of you guys have seen before. And it's okay if you haven't. But they have an awful lot to do with this exponential stuff that we're going to dive into on Friday. Okay, so we are certainly getting near the end. Just as a reminder, you can put it in your calendar now. Our final exam is May the 16th from 1 until 3 in this room. Okay. All right, so on page 39, we'll start with number 1. Can we go to Brian? All right, so take a look at the factored form that we've got up here. We've got some number a sitting in the front times x minus a 0 times x minus another 0 times ... And we know that it's always x minus the zeros, right? Okay, so that's the goal, is to write any polynomial like that. We'll go to Katrina. Okay, so I know that definitely it's going to equal x minus some number, x minus some number, right? How do I know there are going to be 2 factors? Because it's x squared. However, whatever that highest power is, that's how many factors we're going to find. It turns out there is a number, you know, this a that we can stick in the front, there's that a. It turns out that a is the same as the number touching the x squared. We've been calling it a for a long time now. So, okay, I'll put it there in the space. But that's not the important part. X minus something, x minus something. That's the goal. Go ahead, Katrina. Okay, so let's see if we can find the zeros right now. So I'm solving this equation, making the stuff equal to 0. What should we do to both sides? Subtract 1. So far, so good. So we get -1 equals x squared. Then what do we do to both sides? Then we take the square root of both sides. So square root over here, square root over here. What did I forget to put in at that moment? Plus or minus. When you take the square root, you put in plus or minus. Which makes sense because we knew we needed 2 answers, right? You guys told me we were going to get 2 answers. So that plus and that minus, those are my 2 answers. Okay, now we get to something awkward. X equals plus or minus the square root of -1. And it's awkward because the square root of -1 doesn't have any meaning, right? Is there any real number you can take and square it and get a negative? No. Right? No matter what real number you take, if you square it, it's always positive. How much is 7 squared? 49. How much is 0 squared? 0. How much is -2 squared? 4. No matter what you get, it's not negative, right? There's no way to get a negative answer. Not in the real numbers. But now we are going to expand our horizons, and we're going to give meaning to that thing which has no meaning at this moment in time. We're just going to give it a name, a letter. What letter are we going to use? I. Let I equal the square root of -1. It's a number. It's a symbol representing a number. What other number has a letter attached to it? Pi, right? You guys are comfortable using the letter pi to represent that number, 3.14159265358879223. I could have just made those up. You have no idea if those are right. So you're comfortable using a letter for a number. Here is a letter for the number. The square root of -1 is a perfectly legitimate number. It's unfortunate. We use the letter I to stand for what word? Imaginary. That gives it this context that it doesn't exist, that it's less legitimate than the real numbers. It's simply not true. Historically, when they were invented, people laughed at it and said, well, there's no way you can have the square root of -1. It must be imaginary. So like, I mean, really, like 500 years ago, they said, well, it's imaginary. Let's call it I because it doesn't exist. We're stuck with that name, but that is a perfectly legitimate number, the same as 7 is a legitimate number, okay? All right, so what does that mean? It means that our two answers here, we figured out that x was plus or minus the square root of -1. That's now really plus or minus I. So that means my two answers are x equals positive I and x equals negative I. Those are my two zeros. I is the, okay, we got too many questions right now. I is the square root of -1. I is not equal to -1. I is the square root of -1. We can't graph I on the real number line. You guys know this number line really well, right? 0, 1, 2, -1. It goes forever, both sides. All of the real numbers are on that line someplace. I is a different kind of number. It does not live on that number line anywhere. Just it's not there. If I wanted to, in fact, in my pre-calc class earlier today, we said, okay, so that's the real axis. We then drew another thing here called the imaginary axis. And it's got the same numbers, 1 and 2 and 3, but it actually stands for 1 I and 2 I and 3 I's. We're not going to do this here. I'm just telling you what we did pre-calc earlier today. And so, sure, can I plot I? You bet. It's right there. But it's not on the real number line. We need to expand. Okay, so now that I know that the two answers to this equation right here, 0 equals x squared plus 1, the two answers are I and negative I. Well, I know that I can factor x squared plus 1, x minus each of the zeros, x minus I, x minus negative I. That's factored. Okay, let's go to the next page. Now we're on 3. We'll go to Joe. Okay, let's take a look at this next part A. It says, what is the square root of -49? Up until today, in this class, we would just say not real or doesn't exist. But that's because we had limited vision. We didn't understand this whole I business. It's perfectly good now. Here's the rule that Joe just read. If you have a negative inside the radical, you stick an I outside, and then you copy the number without the negative sign. Root -49 is the same as I root +49. Hazen. It is 7i. Normally you can't go any further. This one you can because square root of 49 is nice. But that's the important step right there. Are there questions on what we did? Yeah, so the square root of -1 times the square root of 49. Is that what you said? Yeah? Yeah, because we know that when you have two radicals multiplied, it's okay to put them together, right? That's a rule we know from before. Okay, but Hazen is right. We probably should write this as I times 7. And then generally, if it's a nice number like 7, you stick it in the front and you put the I at the end, but I times 7 is fine. How about the square root of -73? What goes in the front? I. You copy this square root, positive 73. It's done. Don't do anything else. Can't go any further because 73 is not nice inside the radical. You could do this. You could put the I at the end, just like we did before. They're both equal. They're both fine. Generally, it's a little bit dangerous to do that because if you're kind of sloppy with that square root symbol, what might it look like? Like square root of 73i. That I is definitely outside. So either way is okay. Just be careful with that radical symbol if you're going to write it that way. Now we come to part C. I squared. Take this guy, square both sides. The left side is I squared. How much is the right side? -1. So what is I squared? It is -1. Okay? All right, if your calculator is handy, you can take it out. It's okay if you don't have one with you right now. This will be brief. If I type in I squared, I'm hoping the calculator knows it's -1. First thing we need to do is find the I button. Anybody find it? Yeah, there's one at the bottom. There's also one on the x squared. It's green. You guys see the letter I right on the x squared? Okay, that is not the I that we're talking about. The I that we want is lowercase. It is always written lowercase. It is down above the decimal point. So if you type in I, and then you square it, what did we say it was equal to? -1. Does the calculator know that? Yes. So that's the I button down there at the bottom. All right, let's come down here to number 5. And I think we'll go to Hazen. Okay, so here are some complex numbers. 2 plus 5i, 3 minus 4i, 5 plus 0i, 0 minus 7i. Standard form for a complex number is what Hazen just read there, a plus b times I. A is called the real part, b is called the imaginary part. So for 2 plus 5i, what's the real part? 2. What's the imaginary part? Just 5. The I is implied when I say imaginary part. You can just say the number 5. So what's the real part for this 3 minus 4i? It's 3. What's the imaginary part? -4. Include that negative sign. Okay. How about for this next one? What's the real part? It's 5. And the imaginary part? 0. Okay, so that's just plain 5, ordinary 5, which means that 5 is actually a complex number because you can write it as a plus bi, 5 plus 0 i's. So I don't know if you guys have any experience with Venn diagrams. Did you ever play with these things? You got this set of all numbers that we knew until just this moment called the real numbers, but it turns out there's a bigger set called the complex numbers. And all the reals are inside of there because of what happened here with the number 5. 5 is perfectly good. I can say that here's the number 5. And out here I can say is the number 2 plus 5i. It's not a real number because it has i's in it, but it is part of this larger set called the complex numbers. Okay, 6 is a technicality. In fact, we're going to skip it. Let's go to 7. Sam. Okay, we're going to skip these guys right here. I'd like you to be able to do them, but there's tougher stuff that I want to make sure we have time to get to today. I'll practice with these things later on. It's the arithmetic of complex numbers. How do you add them? How do you subtract them? How do you multiply them? How do you multiply these? Something special is going to happen in part E. And then finally, division. It's written up in the textbook. Ask me, during office hours or in the studio if you need help with that, but practice it. I don't think it's hard once you get the feel for it. But let's just jump down to number 8. Eliza. So we've seen this before. Some number in the front, x minus each of the zeros. X minus, x minus, x minus. And then the idea here, is there a question, guys? The idea here is this last sentence, the important thing, Connor. Okay, so what that says is what you guys knew to be true on this previous page. When we had x squared plus 1, how many factors were we expecting? 2, whatever that degree is. That's how many factors you will have, which is the same as how many zeros the thing has. You make x squared plus 1 equals 0, you're going to find 2 solutions. Whether it's easy or hard to find them, I don't know. But you will find 2 solutions. And if I give you some crazier equation, like x to the 7 minus 5x to the 6 plus 8x minus 10. How many solutions does that equation have? 7. Good luck finding them. I can't really help you there, but I can tell you there are 7 answers. But the fact is that some of those answers might not be real numbers. What might they be? They might be imaginaries. In fact, there's a pretty good chance some of them are going to be imaginaries. Okay, so I know that there are 7 answers as long as you allow these complex numbers into the picture. If you don't allow them, then you might not have 7 anymore. It's not necessarily 7 real answers, but there's going to be 7 numbers, including the complex numbers. How about something like this? X squared minus 4x plus 4 equals 0. How many answers will that have? It'll have 2. This one factors. Does that one factor? X minus 2 and x minus 2, right? That's how that factors. So what value of x makes the first thing 0? 2. What value of x makes the second thing 0? 2. How many answers does it have? It has 2. If I said, solve, you would probably just say x equals 2. That's your answer. But how many answers does it really have? Well, naively, it has 2. I can see them. It happens to have the same number. And that's what Connor was talking about when he said, as long as they're counted according to their multiplicity. So we're going to get a full-on 2 answers as long as you allow repeats and as long as you allow complex numbers. Again, what's the name of this theorem? That's the fundamental theorem of algebra. How many fundamental theorems of algebra do you think there are? There's one. It's that one. It's an important one. And finally, we get to it. Whatever the degree is, that's how many zeros the thing has. No more, no less. All right, let's try number 9. Megan, are you ready? I think we're on 26. I'm not even close. 41. Please. Okay, let's pause right there. How many zeros will it have? 3, whatever the highest power is, which means this thing is going to equal x minus 3 things. Yes? 3 zeros, hand in hand with 3 factors. Let's be clear, there is a number that goes in front here. It's always the leading coefficient. What is the leading coefficient originally? It's a 1 in front of that x cubed, right? You can just copy that. It's real easy to forget to do that, so I try to do it first. Whatever number is in front of the leading term, stick it in front of your factored form. That's fine. Okay, so we're going to have 3 zeros for this function. Let's go to the next part, Eric. Okay, so the goal is what's up here in red. Once we fill in the blanks. To fill in the blanks, we need to find 3 zeros. To find 1 0, well, to find any zeros, you're after taking this thing and making it equal 0. Can we use the quadratic formula? Can we use the quadratic formula? No, it's not a quadratic. It's cubic. Is there a cubic formula we could use? Yes. Do any of you remember it? No, for shame. I don't remember it either. So we can't use the quadratic formula. We can't use the cubic formula. Can we try factoring it? That's the ultimate goal. I mean, if we could just factor the thing by looking at it, then we'd be in really good shape for this problem. So what we're going to do is find one of the zeros graphically. Now on a test or quiz, I'm going to give you that hint. I'm going to say, hey, I'm expecting you can't do anything without the graphic calculator to start the problem. We're going to do a lot of algebra to finish the problem, but to start the problem, we need help. So let's take the calculators out. Again, if you don't have it with you, it's not a big deal. We're just after trying to get one answer. How do I graphically try to find one of these zeros? So we're going to look at the graph. So we're going to type that function in. Okay, so we graphed the thing, and we're looking for zeros. But you remember that there's something nice about zeros in terms of the picture. Where do the zeros show up on the picture? Not at the origin necessarily, at the x-axis. The zeros show up as x-intercepts. This is something that we saw last class. So solving the equation equal to 0 is the same as finding points where the graph hits the x-axis. And I see 1. How many am I expecting to see? You're going to get 3. That's the fundamental theorem of algebra. Whatever that power is, I will find 3 answers, 3 zeros. 3 x-intercepts? Not necessarily. Could you tell me where the other 2 might be? They might be imaginaries. They also might be off the screen 100 miles to the right. Right? This graph could eventually come back down and hit the x-axis a few more times out here. And you can try scrolling to the right and, eventually maybe you'll find it. But if they're imaginary numbers, if the other 2 answers are imaginary numbers, you won't see them. You'll never see them because we're graphing only real numbers here. So what we're going to do is we're going to find that first one just by looking at the picture. Then we're going to do some algebra to find the other 2. Just counting hash marks, what do you think x is right there? Looks like it's -3. So we'll say from graph, x equals -3 looks like an x-intercept. Is there a way for us to know whether or not it really works? If it's true, then x equals -3 should do what when you plug it in? Should equal 0. That's what we're after. Looking at the graph, I couldn't tell the difference between -3 and -2.99, but the equation's not going to lie to me. So how about we try plugging in x equals -3 into the equation? So here's our check to make sure that we've got it right. And so certainly there are ways on the calculator to verify this as well. -4 times -3 squared plus 5 -3's plus 78. And so we do this calculation. You can use your calculator. If you're really cool like me, you do it in your head. And you get 0. So we know by plugging in that -3 actually was right. It wasn't -2.99. It's really -3. Okay, so what does that mean? Well, I've got part of my answer. What can I put in one of my red factors? Just got -3. I'm going to put a -3 up there. It will become an x plus 3. But my first time writing it, I always write x minus, x minus, x minus. They're all minus. So that's my first answer. So let's see if we can figure out what's left. What I know is that x plus 3 is a factor of the original, yes? It goes in evenly. Remember what we did last class to try to figure out what's long division? We're going to do some long division. So let's do long division. The thing on the outside is what? X plus 3. We know it goes in evenly. What's on the inside? Whole big thing. Somebody remind me, x cubed. Thank you. If we do everything right, what should the remainder be when we're all done? It should be 0, because we know that this goes in evenly. It's a factor. Okay, so check with your neighbors, see if at least one person at each table remembers how to do this long division carry it through. If you get 0 at the end, you probably did it right. Can we just take one quick detour to the previous page? Brian found a mistake in my answer key. In the middle of the page, you see that row of answers. In part D, I have -12. It should be -13. Is that right now, Brian? Thank you. Okay, so let's come back and see if we can finish this. So we do our long division. Are we surprised to get a remainder of 0? No. If you did not get 0, would you be surprised? Yes. Go back and fix your mistake. If you get anything other than 0, there's a mistake somewhere. So we get our 0, and what's left over is up on top in blue here, is this x squared minus 7x plus 26. And now we take it and we make it equal to 0. We've been trying to make the thing equal to 0 from, for the whole time. Now we have something that's easier, something we can deal with. And so to solve this equation, use the quadratic formula. I'm not going to put all the details. We'll just put the final, well, almost the final answer. Tell me if that's okay. Is that right, people that got this far? So you use the quadratic formula, you get this thing. And now that square root of -55 used to be doesn't exist or not real. What is it now? I square root of 55. It's just changing the symbol. Negative comes outside and becomes an I. And so that's it. These are our two zeros. 7 plus I root 55 over 2, and 7 minus I root 55 over 2. And once you know your two zeros, remember the goal from up above was to write the thing in factored form. I'll go back to my factored form. It had some blanks in it. I started off with 3 x minuses. One of the zeros was what real number? It was -3, so we put it. I think I need a little more space. Let me give myself a little more space. X minus. And we just found 2 more zeros. These are the things that you found from the quadratic formula. 7 plus I root 55 over 2. That goes in one of the blanks. 7 plus I root 55 over 2. What goes in the other blank? 7 minus. 7 minus I root 55 over 2. If we had looked far enough to the right, would we have found the other 2 x-intercepts? Never. They were imaginary. So you find one somewhere on the, hopefully on the window. Do your long division, do the quadratic formula for what remains. That gives you the other ones. Questions on the process? So they won't line up here. Again, in my pre-calc class earlier today, we looked at plotting imaginary numbers. And so we had this kind of funny axis here. And so one of the numbers was what? 7 plus I root 55 over 2. Okay, so this is not something we need to worry about, but we can answer this question real quick. We split this up into 2 fractions. 7 over what? 2 plus root 55 over 2. I'll stick the I at the end. Splitting it into 2 fractions. The real part is 7 over 2. That's 3.5. I can go out here. That's 3. 3.5 is maybe there. Root 55 over 2 as a decimal. I mean, you could type it on the calculator if you want. I don't know. It's like 3.8 or I don't know, something. Type. So we're out here at 3 something, and we're up here at 3 something, and so that number is plotted right there. But it's not plotted here, because here the x-axis is the real inputs and the y-axis is the real outputs. So it looks like the same thing, but it's just different. All right, so we have factored that thing and it's good, 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 good. Can I ask why nobody has commented on my shirt? All right, so I've got this thing on the back of my shirt. It says my name and it says e to the 2 pi I. Now we have not talked about e. It's coming on Friday, but e is the number. Anybody know roughly? 2.7, wonderful, and change. E is some number, pi is a number, roughly 3.14. I is this imaginary thing. What does it possibly mean to take e and raise it to something imaginary? Who knows? We're not talking about it, but the calculator knows. Can you guys type this into the calculator? There is an E button. It is yellow. Anybody find it? It's right above the division sign. Second E to the, make sure you put parentheses, 2 pi I. 2, where's pi? Pi is above the caret right there. Second pi, and then I was where? Right above the decimal point. E to the 2 pi I. What's it equal to? 1. It's equal to 1. 1. I went to a Rubik's Cube tournament. They said, what jersey number do you want? I said, E to the 2 pi I. I said, okay. Now you guys are in the know. You get it now. Actually, I was voted down on this, but I thought we should put stuff like E to the 2 pi I as our room numbers. Like we're in North 404. We could have been, you know, like E to the 2 pi I, right? People said it'll be hard enough to find the rooms without. All right, let's do one last thing and then a massive group activity. Number 10, where's our reader? I think we're up to Iris. Number 10. Let's pause right there. We just got 2 zeros. I put them in my factored thing up at the top. One of the zeros was here in purple, 7 plus I root 55 over 2. The other one was the same thing, but with a minus. Do you guys buy that these imaginary numbers are going to come in pairs like that? Because in the quadratic formula, what do you have? A plus or minus. And the plus and the minus will make the thing look just a tiny bit different, but they come in pairs. If you know one with a plus, you know the other one must be lurking somewhere because the quadratic formula has that plus or minus. All right, so it turns out that these pairs are important enough to be given a name. They're called conjugates of each other, or conjugate pairs. And so what we're going to do here is 11. We'll go to Sarah. Okay, so let's write this equation. F of x equals. All right, you guys remember the whole x minus stuff, right? Okay, we're going to start filling in our zeros. 1 0 is -5. Another 0 is 7. Last 0 is 3 minus 2i. Have I written this correctly? What's wrong? That 3 minus 2i is one thing. It needs parentheses. Okay, x minus each of the zeros. Wait, so then up above, didn't I need parentheses here? It was a fraction, and you could tell like the fraction kind of separated the self out. There was no problem without parentheses on that one. But down here we got no fraction. So we need parentheses. X minus each 0, parentheses are sometimes required. Okay, now we said that if you have an imaginary number is a 0, then the conjugate pair, the partner, is also going to be a 0. So there's another guy, without me telling you that it's out there, what's the other one that's definitely a 0? It's 3 plus 2i. If you have 3 minus 2i, automatically the partner is going to show up. 3 plus 2i. That 3 minus 2i came from what? Yeah, it's a factor. Somebody used the quadratic formula and came up with 3 minus 2i. The other thing they must have come up with is a 3 plus 2i, that plus or minus. So without me telling you, you know automatically you have one imaginary, you have the conjugate. How many zeros do we have? 4. How many are we supposed to have? This is a degree 5, we should have 5. Okay, I suppose technically you could just make up another 0, times x minus 8, maybe. That's not really what I intended, and probably I'm going to make it so you can't do that. I'll say, equation of this, where these are the only zeros, or I don't know. Like I don't want you to just make up another 0. Yeah. Do you guys buy that you could, for example, take this thing and square it? So maybe -5 is there twice. And that's okay. What's the degree of this thing now? Now it's 5. You didn't have to square that one. You could just as well have squared that one. But you got to square something. You actually can't square the other two. It's true. Why can't I square that one? Yeah, I think if I square this guy, that means you have 3 minus 2i once and again. And every time you have 3 minus 2i, what do you also have? You also have 3 plus 2i. I think by squaring one, automatically you bring in another one. So don't do that. But definitely you can square the first or the second guy. And now I definitely have 5 roots, 5 zeros, and that's a degree 5. What's the last thing I could add to this where it wouldn't change anything? I could put a 1 or 17, any number you want. Okay. Questions on that? Okay, we have 25 minutes. You are going to need them. That group activity that follows is long. Let's see how far we can get.